Hi, everybody. Welcome to part two of chapter four. We're going to pick up where we left off on hearing. Hearing involves the detection of sound waves, which is effectively changes in air pressure that unfold over time. Now, sounds are a little bit more maybe complicated than they seem. Effectively, we deal with simple sounds, pure tones, and complex waveforms. So pure tones just have a sine wave formation. They're basically composed of a single wave form at a particular pitch or frequency. Complex waves are composed of multiple waves emitted simultaneously that correspond to specific sounds like your voice. So your voice isn't the production of a single wave, even though we perceive a single pitch. Rather, it's the additive nature of multiple frequencies that make each voice sound unique. Sound waves involve qualities of frequency, which is the rate of how many cycles something occurs per second that we perceive as pitch, how high or how low a sound is. Amplitude is how loud the sound is, how much energy is present. So a sound's intensity. This word, I know you're saying timbre, but it's actually pronounced timbre. This is your experience of sound as it corresponds to the specific things that make sounds. For example, if you've ever played in a band, you can play a particular note, say G, and if you played this note on a saxophone or on a piano or on a guitar, we wouldn't confuse each instrument as the same source of producing the sound. They all sound uniquely different. That's because of those complex waveforms I've described, that even though they produce the same pitch, the same frequency, they're comprised of several different frequencies that, when they add together, make it sound like a guitar or like a piano or like a saxophone or for any other instrument for that matter. So, timbre is that experience of sound quality from different objects in our environments. This image just depicts what I described a moment ago. So frequency is the rate or cycles of how fast something occurs per second. For men, most voices average around, let's say, 110, 120 hertz or cycles per second, which means your vocal folds are vibrating at about 120 times a second. For girls, it's almost a doubling of that, around 220 hertz. Now, both waveforms in this case are around the note A, just different um, octaves apart, or one octave apart for females versus males. So that just means girls' voices on average are then comprised of waveforms that occur about 220 cycles per second. So your vocal folds vibrate faster. How loud we are is that energy we put behind it, which increases the waveform. So a low waveform would have a smaller wave and a lot of amplitude, a loud pitch, or loud amplitude rather, corresponding to a particular pitch, would just be the energy, the height of the waveform. In complex sounds, it's really the addition of other waveforms that go together to produce the sounds that we hear, or the sounds that you produce with your own voice. Much like vision, we'll first start off by describing how we initially process sound. So we have ears, they're called pinnae, that occur on obviously both sides of your head that allow us to process sound that's stereophonic hearing, that each ear is receiving the sources of sound that help us to hear what the thing is that's produced in our environment. And as sound gets closer to us, it's perceived to be louder, which is closer to the ear. If it's faint and further off, it obviously would be perceived to be far off because it's lower or quieter when the sound reaches our ears. Our direction of sound, how we can turn our head towards where something originates, is due to the timing differential of the waves being detected by each ear, respectively. So if each ear receives sound at the same time, we may argue, well, it's in front of us. If it's occurring at our left ear a little bit faster than our right, that's where we directionally think, oh, the sound's coming from the left, or vice versa for the other side. So really, which ear detects sound first indicates the direction of where it comes from. Now, how do we process sound waves to ultimately hear the intricate sounds of our world? Your ear is divided into three distinct parts. We'll start with the outer ear, then discuss the middle ear, and finally the inner ear. The outer ear is the pinna, and the pinna is effectively just the structure that captures sound that funnels it into your ear canal. And at the end of that, we have your ear drum. So you can see here, as you listen to something like a guitar being plucked, the pinna captures those sound waves, funnels it into the auditory canal, and it reaches our tympanic membrane, which we call an eardrum, on the inside of the middle ear that we can't see. On the opposite side of the eardrum is your inner ear, middle ear, and then our inner ear. And the important structure of the middle ear are the three ossicles, which are the three smallest bones in your body. It's the malleus, the incus, and the stapes. The stapes connects to the oval window of the cochlea, which you can see in the image in front of you. So sound comes from our environment to our outer ear into the auditory canal. It first impacts the eardrum, which moves just like if you beat a drum. It pushes the bones, which then transfer the energy to the oval window, and then it travels through the auditory nerve via the cochlea. That's a super simplistic way because I left out how the cochlea actually functions, and sound elicits a response to leave the auditory nerve to go to our brain to be processed, but we will get there in a moment. So, similar to light, our brain has to receive information so it can process things that it understands. And this process is transduction. So the inner ear is where, if you will, a magic happens of the first stages of sending signals via the auditory nerve to our brain to process sound. Now, it's kind of weird to think that you hear through fluid, but effectively, that's almost the way that it works. Now, before I really get into the process of the hair cells in the basilar membrane, um, if we come back to the eustachian tube, you can see that is also in the middle ear we're not talking about. I didn't mention intentionally the semicircular canals. Their role is more in balance than it is in um, hearing and understanding sound, but it is still a part of that structure. If you've ever had vertigo, that's calcium deposits that break off in the semicircular canals that cause you to perceive that the world's spinning, when in fact it isn't. If you've ever had an ear infection, it sounds like it dampens or quiets the sound that comes in because there's fluid back there. It doesn't allow the ossicles to move as freely. You can see this bulging on the tympanic membrane, which is why the doctor looks with light into your ear, on your eardrum specifically. And if it's a bright white light, that's normal. But if it's bulging and red, you can see that there's something behind. And that's usually indicators of an ear infection. You can also have tubes inserted in your tympanic membrane, which is done by an ENT, ear, nose, throat specialist, that can allow the fluid to drain from your ears if you have recurring ear infections. But that's effectively what that is. It's worth pointing out because I'm sure you saw this and had questions. But sound itself from the ossicles attaches to an oval window of the cochlea. And inside the cochlea, it's a fluid-filled chambers. But there's also a section between the fluid-filled chambers that contains the basilar membrane, which is a structure in the inner ear that undulates when vibrations from the ossicles reach the cochlear fluid. So effectively, the sound waves travel through the fluid and they peak at a certain area. And when they peak, think of it as they push up against or they're pulling these hair cells. And when they do that, it causes them to fire, meaning they're sending a signal like the rods and cones. These hair cells are going to bend and they're going to transmit the information about where on that tympanic membrane the sounds have peaked, contributing to pitch. also to amplitude. So if it's where it fires on that membrane, that's going to correspond to pitch. Think about the height of the wave. That's how we perceive how loud something is. And if a sound is extremely loud, this is where hearing damage can occur because it can be so much pressure going through this fluid-filled chamber that if it damages your hair cells, it causes you to become deaf. So the waves travel like a wave through water. If you've ever drawn a bath and just put your hand in and gently pushed against the water to mix up that warm water with the cooler water that first went into a tub, you're sending a wave through the water, just like what's happening in your ear. Now, the inner hair cells are highly specialized receptors that encode information about the sound it's processed from the environment. So the auditory transduction occurs where these cells effectively it's where the wave peaks. Just kind of ignore where the labels are. And this is an overly simplistic depiction of the cochlea rolled out, which you can't unroll the cochlea. And it's just showing you how the sound is traveling through fluid. Obviously, they're not showing the hair cells here. They're just showing the wave through fluid, which would then pull or push up against different hair cells depending on where they are. And our brain would then interpret the sounds correspondingly to where they originated from here. The really neat thing about how our brain organizes and processes sound is that there's a tonotopic map. Now, visually, we also know there's a large degree of organization in the visual cortex, but now we're into sound. And the way that the cortex, the auditory cortex, has evolved is in a highly organized manner, meaning the frequencies aren't haphazardly encoded in the auditory cortex. They're encoded in order of frequency from lower all the way to higher. And you can perceive a range of sound between about 20 hertz and 20,000 hertz. Beyond those frequencies, you cannot detect them. So certain species are highly sensitive to other sounds that they can detect, like a dog whistle. If you've ever heard one, well, that's just it. You can't. So if you blow into this device, we don't hear anything, but dogs can detect it. That's where they'll turn and usually get their attention and look at you. So the auditory cortex itself has two streams, a spatial where things are that occur, so the source of the sound, which is the back caudal part of the auditory cortex, and the non-spatial of what it is, which helps to locate the temporal aspects of time and how we can break up these sounds to understand things like speech or music. Sound is first processed in area A1 of the auditory cortex, and then it continues to other areas to further be processed to understand what it is. So the sensation is taking this sound wave through a process of transduction that allows our brain to send or at least receive signals from our ear about what the source of the sound is, where we perceive what those things are based on the frequencies of firing. The auditory nerve, when it's sending signals to our brain, it's really about the pattern of firing as it pertains to things like pitch and where in the cochlea the frequencies peak corresponds to different pitches from basically the bottom to the top of the apex of the cochlea if we could unravel it and show you the whole basilar membrane. So kind of think of it like a diving board. When you step on the base of the diving board, it's really rigid. It would take a lot of energy to move that base. So if you jump when you just step up on it, the board doesn't really wiggle a lot. But towards the end, you can see how when you step on it, there's a whole lot of flexibility. Now, it's something like that, except that it's ordered in terms of frequency and where the cells correspond to the peak of the wave that travels through it relates to the sounds that we hear. So, really, loudness is signaled by the total amount of activity in the hair cells, whereas the cochlea can register low frequencies via firing rates of action potentials entering the auditory nerve to be perceived as something that's quiet. So, in time versus in pitch or in loudness, it's all the amplitude of where and when things occur in the basilar membrane to perceive the various sounds that we hear. When we want to understand how we hear, we can do so through monaural cues, just one ear, or binaural cues, which obviously involves two ears to help locate what the source of sounds are. The folds of the pinnae emphasize some frequency components over others, and sounds arrive a little sooner at one ear source, really relative than the other. And if something is sooner to the ear, relative to the source at the far side of the ear, it can help us, like we discussed earlier, detect the source localization of the sound, as well as things about how close it is to us or how far it is. High frequency components of sound are more intense in the ear closer to the sound than in the ear further away, because our head creates this acoustic shadow or blocks some of the sounds. As a consequence, that changes the delay at which one ear receives sound than the other. Our perceptual system then organizes and automatically delivers the interpretation of these signals in the most simplest and meaningful manners to process the sounds that we're presented with, which is consistent with our expectations based on our experience of sound. Sounds are often perceived as coming from a single source, similar in its physical properties of frequency or intensity, similar in loudness, pitch, timbre, location, as well as starting and stopping together. Over time, it is not surprising to think about what happens to these hair cells. And hearing loss really has two main causes. One is damage to the eardrum or the ossicles of how the bones can transmit that signal to the oval window to eventually process the sounds that we're hearing, as well as sensorineural hearing loss, which is damage to the cochlea or in the cochlea, where the hair cells, if they're damaged, results in the inability to perceive different frequencies of sound. So remember, we can hear from 20 hertz to 20,000 hertz. But if the hair cells for the upper limits get damaged, this is really where hearing loss comes in, that people find it difficult to hear those sounds. In fact, it's impossible to hear them. So as a result, we'll have the ability to overcome them. So, like with our eyes, we wear corrective lenses. And if you have difficulty hearing, you can wear devices that will increase the amplitude of sounds so that we can better hear um, through hearing aids the various sources of sounds that we listen to. There is also the ability to have cochlear implants, which is an electronic device that can replace the function of hair cells altogether. And it can help with hearing loss, and it can also assist in normal language development. But it's important to note that the sounds produced with a cochlear implant aren't nearly as sophisticated as the sounds that are being processed naturally by your ears. And you've probably all seen the videos where individuals are able to hear for the first time. They're really remarkable. And when you give a baby glasses for the first time and they can see and how their face lights up when they recognize their parents, similarly, it's the case when they can hear for the first time and how parents and the child interact with each other and how they learn to then develop speech and articulate words more consistent with how we would expect you to articulate them. It's truly remarkable when you see how these skills improve, as well as identifying the challenges that can occur if you're unable to hear sounds, but yet still able to overcome this by learning how to articulate sound into words that we can comprehend. There are many other pieces of sound that like we're really not addressing right now that I'm wanting to say, but I think for the sake of time and for not giving you information that won't necessarily be tested, it's probably best just to leave it for sensation and perception or even human neuropsychology if those are topics that you would like to learn more about, sound, in particular music. But maybe I'll just leave it to the source of the lecture itself. The reason I want to say more is the area of my specialization is in auditory processing of sound and training in musicians and non-musicians in motor control and controlling your voice while you sing. And as a musician myself and love playing guitar, there's lots I could say here, but I'll just reluctantly leave it at that. The body senses. So we'll skip away now from hearing. And as much as I would love to go on into more, the reality is most of the chapter, just like much of the sensation of perception course, deals with vision because it's the sense that we all rely on the most. I'm not saying we don't rely on hearing, but there is a lot less dedicated to it. Just believe it as fair enough. But the body senses are also pretty important because when you think about it, the largest organ you have is your skin. And the sensory receptors that we have are in our muscles, they're in tendons, joints. I mean, think of the information you get when you extend a joint too far. You perceive that as pain. So these are able to detect the limits of where we should be moving, say, naturally, and can alert us when things are getting to a point where we could get into a problem if we continue to put excessive pressure on the skin or on the joints. So we are aware of our body and where it is proprioception and say in space. Somatosenses are body senses, and there's haptic perception, which is our active exploration of the environment through touching and grasping objects with our hands. So without even moving through the rest of the slides, think about where the majority of the receptors you have are allocated throughout the skin. Unsurprisingly, if we're feeling and touching objects, they're on our fingertips. Your lips also contain a significant number of receptors. And think of how important it is to detect things like temperature before we consume food so that we don't harm ourselves. So when we think of touch response receptors include pain, pressure, texture, patterns, and vibration. We also have thermoreceptors that respond to temperature changes as well. It is worth noting, though, that you don't see receptors for wet, do you? But yet you've all felt wet. I'll leave that more for sensation and perception, but I just wanted to throw that out there. When we talk about touch, the left half of the body, unsurprisingly, to contralateral control, is represented by the right half of the brain and vice versa. So different locations on our body project to different areas of our brain. We also have distinctions about what and where things are in relation to how we touch and process the information in the environment. The receptors themselves are embedded in our skin and at different depths for things that depend on what the nature of the thing is. So, texture and pattern receptors you can see are near the surface. We have pain receptors a little bit deeper. And think of pressure as someone shakes your hand. We don't expect that to hurt right away, but if you apply too much pressure, now we're getting stimulation because those receptors are firing. They're sending information that, hey, there's a lot of pressure here on, say, your hand. And if you squeeze even harder, what's going to happen is you get into these pain receptors that are really deep in our cells that are indicating, no, this is not good. This hurts. That we want something to stop. We also have deep in our skin receptors for vibrating, for frequency at low and very high frequencies as well. I remember when we had the opportunity in graduate school to teach elementary kids about psychology, I would ask the kids, if I could take away your ability to perceive pain, would you want me to do that? Some kids would respond, no, but most of them said yes. In fact, one kid said, yes, because if I got stabbed, I'd be like Superman and I wouldn't feel it. And all the kids laughed when he said this, but I had to remind them, you're right, you wouldn't feel it, but you would still die. You're not Superman in that instance. You just don't feel pain. So I'd ask them, what's the purpose, do you think, of feeling pain? Now, pain indicates damage or potential damage to the body. If it's tissue damaged, it's then sending signals to our brain through A delta fiber pathways. That is that quick, sharp pain that we experience when something happens. But you also have probably noticed when you've harmed yourself accidentally, but you have this dull pain that comes in later. Those are because a different pathway are sending signals. It's called the C fiber pathway. And that dull ache and pain you feel is because they're active. So there's only two pain pathways. One sends where the information to the somatosensory cortex, so where is hurt or where we should be paying attention. And the other sends motivational or emotional information to the hypothalamus, the amygdala, the frontal lobe of what should we do. So what's that sense of pain? Because remember, pain is pretty subjective in the sense that the pain you experience may not be the same level of pain somebody else does. For example, you've probably all had to have a needle before. Some people, they have needles, no big deal. Some people see needles and faint. Some people, have a needle and experience significant pain. So that's important to recognize is that pain itself is subjective. And part of that subjectivity is how our brain, through different era signals, different areas, are allowing us to experience what's about to come. So these two pathways are they're similar in location, but they are distinct roads, paths, if you will, that are transmitting to different areas of our brain about the where it is and our overall feeling, that subjective experience of how it hurts. You may have also heard of referred pain. This is especially true if someone's having a heart attack. You don't actually experience pain in your heart because the receptors, they're just not there to signal pain. So the referred pain is this experience of pain when sensory information from internal and external areas converges to the same nerve cells in the spinal cord, but it's experienced somewhere else in the body. Pain intensity itself is subjective, and the thought of why pain itself is perceived differently is through gate control theory. So, signals that arrive from pain receptors in the body can be stopped or gated. Think of a gate that's closed by interneurons in the spinal cord via feedback from two different directions. But if that gate opens, it's going to allow these signals to go through, and that would then speak to the ability to perceive pain. So think of a topical anesthetic or a localized anesthetic. What's happening is the signal can't be sent. Effectively, the cells can't communicate that there's pain. So if you've ever had a small procedure done where a doctor has inserted lidocaine in a particular site, so localized anesthetic, you'll notice that if you cut yourself, they can stitch you up and you won't feel the needle passing through your skin. When that wears off, of course, the pain will be sent, where you'll be like, obviously it hurts, but in real time, when this happens, there's nothing. So it's effectively blocked. It's unable to send signals. Brain's feedback to the spinal cord comes from a region in the midbrain called the paraqueductal gray. The pain signals themselves can be suppressed through experience of pain, so we learn to modulate it. But under extreme conditions, really high stress, you get things like endorphins that are active, which inhibit signals to the spinal cord neurons. So it's not uncommon if people get injured that they don't notice the pain right away because of how stressful the situation is. And as a result, it's not until later that they do experience the pain that they're feeling, really when the adrenaline wears off. So pain signals can increase pain sensations as well. Think of things like infection or learned danger signals that we experience. The receptors also help provide us where our body is in space and how we can move and control these movements to execute highly precise and very challenging tasks, like in this case, serving a tennis ball. So, our receptors provide information we need in order to perceive our position and movement of our limbs, head, and body. And as I mentioned just briefly, but the vestibular system of the inner ear, these are the three fluid-filled semicircular canals and adjacent organs located next to the cochlea in the inner ear that help to maintain feedback and balance as we walk through and move through the environments. The chemical senses, adding flavor. Think of how important it is when you walk into a room and you smell something that's delicious and the response accordingly that occurs. Think about when you eat that food and how good it tastes. That is because of the odorants released in the air. They're soluble. They have to be to pass through the nasal membrane to be processed to detect the smells in our environment. It's actually really interesting that when you smell something versus sniffing something, even though it's still using your nose, but those two behaviors end up with different underlying neurological representations to sniff out versus smell or just breathe. You can also think of how important it is to be able to breathe through your nose easily, because if you have a cold, how well do foods taste? They probably taste as you're thinking differently. So, smell and taste produce our perceptual sense of flavor. Odorant molecules travel to the nose through the olfactory epithelium, where they bind to our receptors. So, that's why things have to be soluble because they have to be broken down by the receptors in order to determine what they are, to initiate the sense of smell. So these olfactory receptor neurons then send axons to the olfactory bulb and converge on the glomeruli, which help send and learn the pattern of firing of different smells that we process in our environment, which I realize I'm saying an awful lot today. So the brain structures themselves are located above the nasal cavity, beneath the frontal lobes. So when we smell something, you can see how the odorants in the air pass through the nasal membranes, stimulating these glomeruli, which then send information to the olfactory bulb, to the olfactory cortex, and we process what they are. And think about how powerful that is. When you've walked into a restaurant and smell something, maybe it reminds you of a time when for me, it was like baked bread. Every time I walked into whether it's a bakery or into someone's house who's been doing it, it reminds me of my grandmother, of my mom making bread growing up. It also reminds me of smelling perfume by certain older ladies, typically when I'm walking around through the mall. And it reminds me of how my friend's mom always wore the same perfume. Think of how strong our sense of smell is and how it activates memories just instantaneously, effortlessly. That's because remember, they're not going through the thalamus. This is going directly to the amygdala, which helps us to feel. And it's associated with our memories of feeling of things. The output of smell, or the final stage of the olfactory bulb processing, is in the axons that form the olfactory nerve. And these go to various brain centers, including parts that are responsible for controlling our basic drives, our emotions, and our memories. Now, chemical odors may affect sexual behavior. This is pheromones. It's more commonly the evidence will be supported in animal literatures, but not so much the case for humans. In fact, we're really one of few species that masks when females are ovulating. It's we can't detect it, not reliably. So biochemical odorants emitted by other members of a species can affect animal behavior or physiology. So it can help elicit that it's time to mate in order to reproduce. One of the primary responsibilities of taste is to identify what is harmful in our environments. I often think about people who were first to consume various mushrooms. Think of fungi and how challenging it is to eat mushrooms that wouldn't harm you. Now, some aspects of taste perception are genetic. For instance, if you like parsley, then how does that taste when you think about what it tastes like? For me, it tastes like soap. I don't like it. But this is true of most green vegetables. I do find them to be rather bitter, and I don't enjoy the taste. So I've often wondered when you eat celery, as an example, what's it taste like to you if you enjoy it, whereas I really don't like it? So that would be a genetic instance where if things like cilantro, parsley, if they end up like cilantro tastes like soap, if it does, that's a genetic thing. That means the genes expressed in me result in that flavor profile being associated with something that tastes like soap. Whereas if you don't have it, I don't believe it's the case that it tastes like soap to you. There are five main types of receptor cells for taste, the microvilli that are on your tongue, and they are salt, sour, bitter, sweet, umami, which is a savory flavor profile. Um, they're fat, and it's maybe a sixth basic taste by fatty acids, which is distinct from the five primary taste sensations. But really, it's the five flavor profiles that are particularly important. When it comes to your tongue itself, the distribution of the receptors are not equal. They are distributed around and all over the tongue, different areas for different tastes. And some people are super tasters, so they just have more pronounced or more receptors for taste, and others there's less. And you can see a smoothness versus a different, I don't want to call it a rough appearance of a tongue, but the tongue of a super taster is not like the tongue of one that isn't. So there's lots, like thousands of bumps, the papillae that contain the taste buds, which house the receptors that allow us to ultimately taste, along with smell, create the flavor experience we have when we eat food. There are individual differences in taste perception and tolerance, especially of different textures of foods, but also for spicy foods. For some people, pepper may be perceived as spicy, whereas others, jalapeno or habanero peppers, if you're bold enough to try ghost peppers, for instance, there's different levels of tolerance we have for things like this. And then we have tasters that are basically normal people that taste food, non-tasters that have struggled to detect and taste food for various reasons. And then there are super tasters that are really sensitive or able to detect the elements of what's in our food. Gordon Ramsay is a good example of this. If he tastes something through cooking, he's really accurate at identifying all the elements of what's in there. So maybe when you're eating next time, you might think about all the seasoning that's applied to the food. What can you taste? What can you detect as you're eating? That's your ability to perceive flavor. Any food molecules dissolved in your saliva evoke a specific combined pattern of activity in these five taste receptor types that you possess. Food perception is multisensory. It involves taste, smell, and texture. Primary olfactory and gustatory cortex are interconnected, with gustatory cortex passes taste information directly to the olfactory cortex. That's all there is to this lecture. I know I've left a lot out, but I hope rather than leaving discouraged about not necessarily going into more detail, I hope I really leave you encouraged to learn more about them as you continue your undergraduate studies. Nevertheless, thank you for listening along. I hope you enjoyed this chapter as much as I did, and I will catch you at the next lecture. Thanks so much. Have a great day.